Thank you. Okay, can everyone hear me? I can take that as a yes. Anybody know who Qualitests are? Cool, okay. So Qualitests, the world's largest pure-play software testing company. Testing is all we do. We don't build systems. We're not like Accenture or Cognizant. We're not a developer. We're just focused on quality. Within Qualitest, I head up the AI solution set, which means I'm responsible for, firstly, how do we define and identify new practices for the quality assurance and the testing of artificial intelligences, and also how can we use artificial intelligence, machine learning tools to make testing better. And it's about that side of things that I'm going to talk a little bit today. So apologies if I'm teaching any of you guys to suck eggs, but I wanted to start at the beginning with just a recap on what is software testing and some of the challenges that face testing as an industry. A very famous testing guru, a gentleman called James Back, said testing is organized skepticism, the belief that things may not be as they seem or that things could be different. That's not really the most approachable definition, but it's a pretty suitable one. But when we think about it in more practical terms, software testing is generally exercising, exploring, and validating that a system complies with the requirements that originally derived it, whether that's that the buttons all work, whether that's that it does the right thing at the right time. When systems don't do this, we refer to it as a number of things, but usually defect, glitch, bug, fault, issue. There are many, many flavors of software testing. The 6 biggest are probably these 6. So the one that most people have come across is what we call functional testing. If I push the button, does it do the thing? Are all the requirements met by the system? If we input certain types of data, do we get the right outputs? Performance testing is the next one that most people have come across. How many users can access my website before it falls over? Where are the bottlenecks in whatever it is I'm trying to do? If I have to do something like a failover to a disaster recovery site, can I guarantee that my users don't get interruption? Security testing speaks for itself in a lot of ways. Am I encrypting passwords? Do I know that my user data is not being stored insecurely and can't be exposed to third parties? The less common ones are at the bottom, but they're very, very important. Usability. There's a lot of focus on that. There was a quote from one of the speakers yesterday from Adobe, turned around and said, people buy experiences these days, and that's absolutely true. And if your user experience is bad, people won't use your product because it's such a competitive marketplace, there will be competition. Usability is focused on how good's the experience and also how usable is it. Can my users find all the buttons, the functions, what they need to? Accessibility comes hand in hand with it, but it's not quite the same. Accessibility focuses more on can differently abled people still use my system? If I'm colorblind, can I actually distinguish all the parts of your website in the UI? If I'm partially sighted and I use something like a screen reader, does your application tell me everything that's present? Localization is also very important with global sites. Are translations correct for languages? What about things like pricing? Prices can be shown in very different number formats depending on where you are. What about color schemes? Something that a lot of people don't consider is that coloring can be more impactful in one culture over another due to cultural significance on colors. So where does test management come into this? The common definitions of test management refer to the activity of managing the testing process. Pretty intuitive, but generally what we mean by this is establishing and coordinating the resources for testing. And resources is the people, the software, the infrastructure, the data that we're going to test with, the money that needs to pay for the testing, and also working out the focus of testing. How many of those different flavors of testing do we actually need to do? Do we need to worry about functionality alone, or do we also need to consider performance for this release, security for this release, and so on? And what about the entry and the exit criteria? When can we start and stop the testing? When am I happy that the piece of code, the application, whatever it is coming downstream is ready to test? And when do I know that it can go out to the users? And what order and priority do we do the testing in? Now that sounds like a little bit of hassle, but it's kind of necessary. A couple of years ago, we ran a mobile experience survey to our customers that predominantly are app vendors, or for our customers that are predominantly app vendors, and we came up with these numbers. 37.3% of your users will stop using an app when they experience a glitch. Anybody want to put a hand up if they ever used an app again once they'd uninstalled it because it had broken on them? Probably not many of you. 62.4% of users say that bugs and glitches make them worry about app security. Again, anybody here use an app they don't feel secure with. Most people just uninstall them. 82.4% of users have experienced some sort of an issue with app closure, latency, screen freeze, UI error. This is just in the mobile world. So testing, unfortunately, isn't something we can just skip. And we're showing that this idea that you can just fix it in production doesn't work. 37% of your users have already uninstalled it. They're not going to wait for you to fix it, even with the rapid releasing. So how do we make sure that our quality processes get better and mature? When we think about software testing and quality control, we can draw parallels between the way that we check our software control versus how we check the quality of other products in manufacturing, automobiles, those kind of things. In common manufacture, there's about 3 terms that are usually guiding quality assurance: product inspection, process control, and process refinement, design improvement. The first stab at software testing is quite opportunistic. It's product inspection. Basically, historically, it's a case of give me the product and I'll play with it and see whether it does or doesn't do the thing. This is pretty unsustainable. You don't want to do all of your testing at the end. So then we mature to what we call quality assurance, which is the point at which we start defining processes that make better quality go into the product. In other words, we're saying that you will always do this kind of code review, that you will always do this kind of inspection. We're making our process more manageable and sustainable. In other words, we're starting to get a little bit more tactical about how we approach it. The latest evolution, or the highest of the current ones, is what we refer to as quality engineering. And this is where AI starts to come into things. With quality engineering, we're applying engineering as a discipline to keep our processes optimized, to keep tuning them, to keep improving them, and keep engineering them. The process that you wrote in the strategy 5 years ago isn't necessarily still valid today. You need to be prepared to update it. Maybe you focus more on this, maybe you focus more on that. Maybe you need to test in a different way. We can use AI to start to inform it, and we'll come back to that in a minute because that's where we're going. There is a direction here, I promise. What's happening in the world at the moment? So I think there's a few things here that everyone will understand and relate to. In the last handful of years, and I really mean sort of the last 5 to 10 years, we've seen some huge technical shifts. Everyone's on hyper-connected systems. We've had the rise of 3G, 4G, 5G networks. Everyone's talking all the time. So much information is passing. The cloud was a massive success. Big data is a massive success. And we're expecting more and more power in our applications. Artificial intelligence, machine learning is almost becoming commoditized, as is just better experience, better software. We've also had generational shift. The continuous integration, continuous deploy, the DevOps movements have been incredibly successful. We're no longer prepared to wait 6 months, 1 year for that next release of software. We want the software now. We want continuous deployment. We want it in the next week. We want it in the next day if we can have it. I'm sure most of you have seen the speed at which Chrome or Firefox actually push an update. Most of the time you don't even realize you've got the browser open and it's already got the next version for you. But this gives us a problem. We're trying to put in a whole load more stuff. We want it out faster and faster and faster, but we've got to test it. We've established that we can't skip the testing because if the testing doesn't work, if the testing isn't done and the product doesn't work, people are going to stop using it. And so the test managers have the problem that I've got less resource, but you still expect the quality to go up because we've now got that competitive marketplace, because there is an explosion of apps, of browsers, of sites, of technologies. So how do I balance that? Traditionally, testing localized onto what we would refer to as a risk-based approach. In a risk-based approach, you take the likelihood that something's going to go wrong, combined with the severity if it does go wrong, and you use that to order what you want to do. In other words, something like, for instance, my login page not working is a pretty severe problem. It means no one can get into my application. How likely is it to go wrong? Fairly unlikely. It's tested regularly and often. We can take every single feature, every single component, every single test case, and we can score the risk of that piece of the application to turn around and say, this is the order I need to test in. And then we can set a cutoff point, which is anything that is below this risk level. So probably somewhere down here in this green area, or it would be green, except this is a slightly washed out screen. We can probably skip. The stuff up here, highly likely to go wrong, highly impactful if it does go wrong, has to be tested. And every piece of functionality will fit somewhere in this grid, and we can use that to organize our testing. The problem is Working out what the risk is for each component is time-consuming, particularly on large test suites, because we store data in an awful lot of places. You're usually relying on experienced test managers, experienced test leads who know the application. You have to be able to turn around and say, this component has these risks of knock-on if it goes wrong. You need to say the likelihood of this actually going wrong, because we've seen this, we've done this before, is X. This takes time. So whilst we've got an approach to streamlining our testing, we don't actually take away the pain, we just transfer it onto the test manager to come up with a plan for doing things faster. And this is where AI can start to help. Before we talk more about that, I just want to explain what I mean about the amount of different places we store data. In a standard piece of software, you're probably looking at, as a minimum, these 5 families. They're not exclusive. There are others, but these are the main ones. You've got software development systems. In these systems, we tend to track, what was developed, who developed it, why did they develop it, is there a link back to the requirements or the driver for this piece of functionality? In the test management systems, we've got the information about what testing is available to me. What checks do I have? Are my checks grouped? For instance, do I have a nice convenient way of saying these are my performance tests, these are my automated tests, these are my run once a year tests? Where can I execute them? What environments are available to me and what versions of the software are they working? We've got the test result systems. What did you test at what points in the past? Did it pass? Did it fail? Did we do any investigation around why? You've got the defect systems. Speak for themselves. This is the log of issues that we've seen in the past, combined with the severity, the likelihood, the detail. Did a customer find this defect? Did it actually make it out into the wild and we heard about it through a support ticket? Or did we catch this in-house? And you've got the production systems. The process of observing and checking quality doesn't stop just because your code has made it out the door. Douglas Adams actually came up with the quote, if you try and develop a completely foolproof system, you usually underestimate the ingenuity of a complete fool. Now, users aren't complete fools, but they will put the software in situations that you will never consider. They'll sideload it. They will put it with, we've had a lot of conversations about Dockerization. Maybe they'll put it into a container in a hypervisor that doesn't have enough headroom. Maybe they will run it sideloaded with a piece of antivirus software that dislikes something you're doing. Maybe they're on a particular version of their mobile operating system you haven't considered. To truly do risk-based testing, you need to understand what is in each of these areas. You need to combine it all in one place, and then you need to use that to assess the likelihood and the impact of each of the failures that you may find in your software. That's a lot to take on. It's difficult for one test manager. It's difficult for a team of test managers to do that with the cadence we need to be able to release software all the time. So can we do it with machine learning? What if we could optimize the testing process by predicting the cases that are going to fail? We can take that hit off the test managers, and we can speed up the testing process. If we can do that, we can make sure that the testing that is being done in the right areas. Any time saved, we can now focus on better quality elsewhere. So what are we looking for? We talked about that family of stuff. With each of those blocks, we can start to get different bits of information that can feed our quality engineering insights. For instance, if we just have the test information, if we just have the details of the test management, the test execution, we can get test analytics. This is fairly noddy. What's the likelihood a test is going to fail? Are there patterns in my failing test? Is it always this suite, always that component? When we start to combine with other systems, for instance, if we combine some of our development information with our test information, we start to understand what development and test impact will have. For instance, when you put this change in, what did you test afterwards? How long did that take? How many new failures did you introduce? How many tests were introduced? What's the likelihood that a similar change is going to introduce more failure? If we have defect and test data, how many of my tests link to defects? A tester can run through 10 tests and maybe only raise one defect, even though all 10 tests fail, because it's the same defect. How many defects are shared by tests? If this problem is here, how much other stuff does it bottleneck and block? What about severity and priority distribution? How many really big problems are in my application versus how many trivial things I probably don't care about? What about defects that made it live? would any of them have been caught if we tested in a different area? If we can combine all three of those, development, test, and defect information, you start to get overarching insight. You're able to turn around and say, well, what is the likelihood that whatever I am doing up here is going to break something? What should I now test because of that? How many defects do I think I am likely to get here? And can I now time box my testing window? This is starting to transfer into a BI and AI problem. We need a holistic source of truth. We need to be able to turn around and say, I can take all of that information from all the various places you've been storing your information, and I can tell you that selection of insights. Firstly, this is the patterns I see. This is where your defects are usually found. This is where your test issues are usually found. But I can also then start to optimize on that and target that. For instance, if we have that information about where are the tests that pass, fail, etc., we can use that to inform our quality engineering. If I can use an AI, or when we use an AI, to turn around and say, based on all of this information, based on everything I can see about the code change, the test detail, the defect detail, and the last time or times you tried this, this is the likelihood that this test is going to fail. This is where the AI comes into it. Qualitests are using an AI that predicts passing, failing tests based on all of that information. And from that, we can turn around and say, well, why is it that I have some tests that never fail? If they never fail, is there any real value to having them in the test pack? Maybe they need refinement, maybe they're just not looking in the right place, or maybe they can just be deprioritized. They've gone all the way down to that bottom left corner of the risk grid. What about the tests that always fail? Are they broken tests? Is that a particularly flaky piece of automation or an unfair test for what we're doing? Are there patterns in the failures? Do all of the failing tests occur in the same part or parts of the application? Can we trace that back to a particular team or component? Maybe there's some tech debt we've got to work on. Is there commonality in failure location? For instance, are certain environments more susceptible or less susceptible to failure and problems? But one of the most important ones is this one here. How long should I spend testing? If I know how many changes are coming, and I can get a predictive model to a good degree of accuracy that can turn around and say, these are the ones that are going to fail, we've got the historic data. We can turn around and say, it should take you exactly this long to test. We also have the distribution from the linked defects. We can turn around and say, this is exactly how many defects I now expect you to find. And then we can say, well, we can then factor in fix and retest time. In other words, we can put a very concise time box on manual execution where it's still needed, and we can inform the automated process to say, these are the tests that you need to automate first, because these are the ones that are always risky. We're trying to lead all the way to shortening that release time. And what about the quality engineering argument? Are there weaknesses in my overall process that I can now identify? If I can see that there are clusters of failing tests, whether they're clustered by tester that always fails them, whether they're clustered by component, whether they're clustered by area or type of testing, we can then use that to inform the process and say, with the time that we can save by not running the tests that we don't need, we can now focus on actually fixing the processes, making better software. What happens when you apply it? So for one of our customers, we were able to get a model that was 80% accurate at detecting the passing and failing tests. We cut their execution down to 1/3 of the tests. That gave them 6 times faster time to release, or 40% efficiency increase in quality engineer. Now, we're not saying you can get rid of all the quality engineers tomorrow, but what we are saying is we can now use 40% of their time more effectively. What would your test engineers do if they could have almost half of their week back tomorrow? That's a huge saving. That then lets us go back and say, let's optimize the process further. But there are some pitfalls, unfortunately. Testing is very, very subjective. Different testers in the same organization will record things in different ways. Different organizations, even though they may have a very similar output, will store the data another way. If you were to go to someone like eBay and someone like Amazon, you would see differences in the way they store the data, even though they're big e-commerce online retailers. If you were to look at the way Google store versus the way Microsoft store, you'd still see those differences. It's highly subjective. Now, Qualitest don't have a boxed AI that we can just give to you, but we've shown that this process works. We work with our customers to identify all of this. The data's rich text. We're a social animal. We are so driven by our language and our communication. We've seen a number of talks here about how do you do NLP properly? How do you do better with poor quality or spotty text data? We have the same problem. If you look at a quality system, you will have standard fields, test priority, defect priority, component under test. But the real meat of what's being tested, the real bit where we can understand what is the test actually doing, is usually in a text description, whether it's a number of test steps that say, click this button, enter that SKU code, click that button, or whether it's in something like a user story. The information is almost invariably stored in text. It's not stored in the fields, although the fields are helpful. Disparate sources. We've talked about the fact that you've got dev information systems, you've got test information systems. Different teams may be using competing software within one organization. We'll go to an organization where you'll discover, for instance, half the guys store the defects and test management in ALM, the other half use Qtest and Geater. There's nothing wrong with that, but it means you've got to work out how to join up that data. If you want that AI, whereby you can say, I can understand the quality all the way through your different sources, you need to join the data up. There's also inconsistency. Big organizations, even small organizations, you will find people with competing standards on how they do things. For instance, two big data test prioritization schemes are P1, P2, P3, P4, and Moscow. We've been to organizations where both of those have been in use in the same organization. In terms of feeding an AI a feature set, it doesn't matter which one you pick, but it needs to be unified. Connectivity and traceability should also be on there. Most organizations have source control data, test data, production data. Very few organizations actually have the ability to trace all the way through. Very few organizations actually have the Git commit message that ties to the Jira ticket ties to the Qtest entry, the Qtest entry ties to the defect log. They do happen, it does exist, but not many people do it. I'm sure any of you from software houses have seen this yourselves, right? Dev guys store stuff here, test guys store stuff there. Customer support, nobody knows what they do. Working out how to get access to all of those systems and follow the data through is difficult. There's also the privacy and the confidentiality aspects. Confidentiality, we're looking at taking insights across people's entire quality gamut, across their entire process. There is, by definition, confidentiality around the IP of the software in there, details of how this particular function was put together. There's also privacy. When we consider that some of what we were talking about was we need post-live data as well to understand what happened. Well, we need to make sure that nothing came back from the post-live data that we're not allowed. GDPR compliance, data protection compliance. And we also need to be careful of the panacea mindset, and I think this is common for all of AI, not just what we're doing with it. It's this idea that AI will solve the world's problems. Whilst the AIs that we develop are an incredibly powerful tool at optimizing your testing, it doesn't remove the need to test. It doesn't remove the need for your quality engineers to focus on other things. It just speeds up the process. So how do we mitigate around this? When we roll out the QualiSense test predictor, we do it in 3 phases. The first phase is what I tend to refer to as the data science. This is just about working out where the customer's data is. What is quality for you? Do you have information in Jira, in TFS? Is it all in old Excel worksheets? Then we need to work out how it all joins up. How do we solve those problems with my guys use Moscow scoring, my guys use this kind of scoring? Feature selection, feature engineering, which bits are actually deterministic? If you think about testing, we're going with historic runs. If we're trying to identify a test that is going to fail, we can't rely on the date the test was executed at last time. That's time-sensitive data, and up front, you don't know when it's going to be. So it's understanding the bits of information that have no relevance. Test identification, for instance, we remove that. But also, we've got to do all that text analysis. We've got to do all of that understanding of synonyms, of the fact that this guy refers to the shopping cart, that guy refers to the basket. We've got to work through all of that. In the second phase, we start to build the models. Now, we've discovered that there isn't really any one AI algorithm that is better or worse for every single customer. When we model for the customers, we actually build several models. We build around about 15 to 20 different models on the same source data. So we will try things like random forest, we'll try things like gradient boost, we'll try things like logistic regressions. And we see which ones start to get closest to the mark. In that second phase, it's all about taking a look at those models, seeing if we can do anything with regard to tweaking hyperparameters where suitable, working with customers to explain that actually no AI is 100% accurate, that we don't want one that's 100% accurate, we want one that can generalize, and 100% accurate is usually just localized on the noise. And helping them understand the point at which the accuracy is more important or good enough for them to use it as a BAU part of testing. In the third phase, we take the software to production for them. The AI model runs on a server instance which is hooked up to their upstream systems, which are then feeding in the data, whatever the sources of data that we identified and joined up were. We pull them into one location, we feed the model so that as something changes, whether it's because Joe Bloggs has checked in a change or whether it's because somebody's written a new test set, the predictions get updated and turn around and say, this is the output now. We also provide a dashboarded output for that, which turns around and says, these are the tests with the probability of failure. This is the groupings. So for instance, the tests in this module are this likely to fail. The tests of this type are this likely to fail on average. This is the number of highly likely failures. In other words, we are 75% or more confident that this is going to fail. This is the number of medium likelihood failures, 75 to 25. This is the ones that we're absolutely sure are not going to fail at all. This is how long we think your testing is going to take. If we take all of these highly likely failures, this is how long those test cases take to run based on your historic data. And this is how many defects you can expect based on the amount of times you link your test cases through. So, conclusions. Software delivery is continually evolving. We've seen that with the rise of DevOps, with the fact that we're all here to talk about AI, which was really just a plaything for academics 20 years ago, and now it's everywhere. We're under ever more pressure to get more functionality, but also get it out faster than ever before. We know we can't test everything. Even with highly parallel automation, even with cloud scaling, even if you've automated 100% of your test cases, and if you have, I'd love to hear that because you'd be the first person I've ever spoken to that got 100% automation. It's incredibly expensive to test everything. We need to test smarter. We can't just test harder. We can't just throw more automation at it. We can't just throw more bodies at it. AI is one avenue that will let us get smarter testing. It helps us speed up the processes we can already do, and it lets our quality engineers then focus on baking better quality into the software in the first place. But it's not a silver bullet. It is a decision support system in this case. How do I help you focus on where you should and should not test? But once you've done that, how do you use that 40% of your time again to make things better going forwards?